Well, here is an important review for exam 2. And I've worked for at least 3 hours on these problems. I'm trying to give you an idea of how the exam is going to look like. So make sure you understand how each question is worked out. And wish you the best on the exam. On the exam, you have chapters 4, 5, 6, and 7. And a few questions from chapter 3. So let's look at these questions one by one. A flywheel is rotating at 16 revolutions per second. Now that is the frequency of rotation. 16 revolutions per second. What is the total angle in radians through which a point on the flywheel rotates in 55 seconds? So you're asked to find theta. So the frequency there is given 16 revolutions per second. Time is 55 seconds. Omega is defined as delta theta by delta t. Angular speed or angular velocity is angle divided by time. So you rearrange that. And omega is 2 pi times frequency, because one rotation is equal to 2 pi. So 2 pi times frequency times dt, which gives you the answer. It's 5,530 radians. In the second question, it's about circular motion. The path has a 7.05 meter radius. And at how many revolutions per minute are the riders subjected to a centripetal acceleration equal to that of gravity? So that's the point. The formula for centripetal acceleration is v squared by r, which is equal to g, because it says it should be equal to that of gravity. So rearrange that, substitute, you would get the velocity. Now to go from the velocity to the angular velocity, we use this formula, and then you get the angular speed. Once you get the angular speed, omega is 2 pi f. So f is omega by 2 pi, which gives you the answer in revolutions per second. But they want the answer per minute, so multiply that with 60, which will give you the rotations per minute. That is 11.3. And then you have this question where the position of a particle is given. It's a function given there. There is a cosine part and there's a sine part, and you're asked to find the speed. Once you have the position, to find the speed, you have to take the derivative. So vxt is dx by dt. So when you take the derivative, you get dx by t, which is d by dt of this whole thing. But remember that when you take the differentiation of cosine, you're going to get negative sine. And then you have to remember there is a 4 here. That multiplied with 2 becomes an 8. So that's why you get minus 8 sine 4t. Do the same for the y. And the y function is given. But this time it's a sine function. So when you take the differentiation, you take positive cosine. And the magnitude would be the square root of the sum of the squares. And when you write this function down, you see you can take out the common factor 8, and then you have sine squared theta plus cos squared theta. Now sine squared theta plus cos squared theta is 1. So that becomes 1, and therefore you get 8 meters per second. In this question, you have the velocity of a particle in a reference frame A, and the velocity of the reference frame A with respect to another frame B is given, and then again the velocity of reference frame B with respect to C is given, and you're asked to find the velocity of the particle in the reference frame C. So it looks like a very confusing problem, but it's actually easy. When you remember that velocity of the particle in frame C is nothing but velocity of the particle in frame A plus velocity of the particle, velocity of frame A compared to B plus velocity of frame B compared to C. So the idea is this. Look at that. You start with P, end with C. So here you see PA and then it's AB. So you end with A, begin with A, that cancels out. Same thing here. You end with B, begin with B, that cancels out. So finally you're left with P and C. So that's what you remember when you take the relative velocity. So now that's given us 4.0 I plus 5.0 J. And then the other two are given likewise. So when you do the calculation, it's easy. But that is an important rule to follow. In this one, raindrops fall vertically at 7.5 meter per second relative to the earth. So here what you have to know is you have the relative velocity of the raindrop with respect to the earth, and there's an observer in a car moving at 21 meter per second along the x-axis. So going by what I told you in the last question, velocity of the raindrops with respect to the earth is given. It's negative because it's coming down along the y-axis. And then you have the velocity of the observer with respect to the earth is 21.0 I because he's driving along the positive x-axis. And then velocity of the raindrop with respect to the observer is what you have to find. So in this case, the relation should be written this way. Okay, so there you see that we start with R, end with O, same thing here. So you see the E's will cancel out. But this term that we have written is not the velocity of the observer with respect to the earth, but the velocity of the earth with respect to the observer. Therefore, when we write it, we're going to say negative of the velocity of the observer with respect to the earth. So, see that? Negative of the reverse. Why did we have to use the reverse? Because that's what is given as 21I. So now all those are vectors, and when you substitute, you get that vector, and the magnitude, just like before, is the square root of the sum of the squares, which gives 22.3 meter per second. And then to find the angle, drawing it that way might be a little... Anyways, what you get is 20 degrees, and theta is 180 plus 20, which is 200 degrees. In a counterclockwise direction, you get 200 degrees as your answer. Which brings us to this question. A telephone pole has 3 cables pulling as shown. F1, F2, and F3 are given in terms of the IJK vectors. You have to find the net force, which is a simple thing. Just, what you do is take the vector sum of all of them. And just like before, find the magnitude. To find the direction, take tangent of the angle. It's minus 34 degrees, but to get the counterclockwise angle, you say it's 146 degrees because you have to add 180 to that. So that is the answer. And then in this question, the net external force on the 22 kilogram mower is given as 50 newtons. Force of friction opposing is 12 newton. How much should the person apply? Quite simple to get this. That is the free body diagram. Force applied by the person and friction is opposite. So net force should be FP minus 12, which gives FP as 62. And then if it was moving initially at 1.5 meter per second and the force is removed, how far will it go? So in terms of work, you get force times displacement is equal to change in kinetic energy. See, that is the work energy theorem. Work done is equal to change in kinetic energy. The work done here is 12 times delta x, because when you remove the force, the only force acting on it is friction, and so friction is the one that is stopping it. So the frictional force multiplied by the displacement would give you the change in kinetic energy, which is 1/2 mass times velocity squared. And then when you do the calculations, you get 2.06 meter. And here you have a car weighing 15,000 newtons, starting from rest, accelerating, friction force is given. Find the applied force in newtons produced by the engine. Find the acceleration using this formula. Of course, 89.0 kilometers per hour has to be changed into meter per second. That's how you get 24.7. And once you get the acceleration, net force is equal to mass times acceleration. Now, once again, it's 15,000 Newton. That's the weight. So to find the mass, you have to divide that by 9.8. That's how I get this number. Mass of the car, okay? And then you know that the force applied by the car, take away the frictional force is the net force, because friction is opposite always. So that gives you the force applied by the car. When you add those two numbers, get 8,811 newtons. Of course, I'm trying to go through this as fast as possible, but you know you can pause it at any point. So let's keep moving. Next question talks about a gymnast of 25 kilogram mass decelerating by pushing straight down on the mat. Now remember that when she applies the force on the mat, there's a reaction of the mat on that gymnast. So the net force in this case is MA, but the net force is the upward force applied by the mat on the person minus the weight, because it's acting down, should be equal to MA. So there you go. The force applied by the mat on the person and the weight. So just rearrange that. And a deceleration is 7 times the acceleration due to gravity. That's why I have that as 7g. And then you have, so 25 times 7g plus 25 times g, that is 25 times 8g, which gives you 1960 newtons. And here you have a traffic light hanging from cables. You have to draw a free body diagram. Well, the free body diagram is right there, because you have the tension 2, tension 1, and you have the weight. So it's right there. Those angles will be 41, 63, because they're going to be alternate angles when you draw a parallel line there. Okay. So that is the free body diagram. Not a big deal. And here we have a fleet jumping by exerting a force straight down, and a breeze is blowing parallel to the ground. So you have the reaction on the fleet upwards and the breeze flowing this way. So you have the two vectors, and this is going to be the net force. Theta is the angle, and I've just, this is the force. The upward one is the force of the ground on the fleet minus the weight, because you also have the weight, right? So I've shown that as the net y. This is the net x. And those are numbers given. That comes out to be 0.62 times 10 to the negative 5. Now, therefore, the net forces, that's the force due to the breeze. It's along the x-axis, so it's I. And then this is along the y-axis. And then the net acceleration is just obtained by dividing it by the mass of the fleet. So once you obtain the vector, find the magnitude. And then find the direction, finding tan theta as the y coefficient divided by the x, right? Which gives you 86.5 degrees. And here is somebody being pulled to the side, and the free body diagram is actually given. And what you have to do is break this up into the x and the y. So when you have this tension, it can be broken up into its horizontal, which is going to be cosine, and its vertical, which is sine. And this one do the same, but be careful, because this angle is going to be 15. So the vertical will be cosine and the horizontal will be sine. Long story short, here are the horizontal components. T2 cosine 10 and T1 sine 15. They have to be equal to each other. And here are the vertical components. There are 3, including the weight, which acts vertically down. So you have T1 cosine 15, and then you have T2 sine 15. So T1 cosine 15 plus T2 sine 15 is equal to the weight, which gives 750 Newton. So now it's just a case of so from the first one, T1 is 3.77 T2, and that's what I'm plugging in into this. for T1. And so that's just T2. So solve that. And you would get the values of T2 and T1. You just have to follow the math that happens there. But it's basically using the X components and the Y components from the free body diagram. Here you have a wooden crate resting on a wooden floor. The coefficient of static friction is given, and question is, what force can you exert horizontally on the crate without moving it? Of course, if it's not moving, it's static friction. Therefore, it should be equal to the frictional force, static friction, which is the coefficient of static friction times the normal reaction, which in this case is the weight. So you get 573 newtons. Now for the B part, when it says if you continue to exert this force, what will be its acceleration? But remember, now it's the coefficient of kinetic friction. So you're going to say, okay, you're already applying this force, minus kinetic friction is equal to mass times acceleration. And then kinetic friction is mu k times n. Once again, the normal reaction is the weight, so you get kinetic friction, plug it back there, and you get the acceleration as 1.96 meter per second squared. This is a very interesting question. The first part is quite simple. The car is moving on a banked road. The banking angle is 15 degrees and the radius is 100 meters. You're asked to find the speed. And you use the formula tan theta is equal to v squared by rg. Make velocity the subject. You would get 16.2 meters per second. Now in the second part, somebody is driving at a very low speed, which is 15 kilometers per hour, which becomes 4.2 meters per second. And so now, because the road is banked, there is a chance that it could slip down. And our question is, what is the minimum coefficient of friction so that it doesn't slip down? So now it becomes a kind of complicated question, because the diagram, let me slow that down and go back. That is the normal force, which is now broken up into the two components, X and Y. And then you have friction, and the friction should also be broken into its components. That's the X and the Y for friction. So you see that you have two horizontal components which together provide the centripetal force, and then you have two vertical components and the weight. So that means these two components balance the weight. That's the weight, okay. So now you have to be careful. That's the frictional force. If that is theta, then this is F cosine theta, and then you have F sine theta. Similarly, break up the normal reaction into its components. That will be N cosine theta and N sine theta. And then take the X and the Y. So this is the X component, or the X components together provide the centripetal force, right? That's the centripetal force. And then you have the Y, which is N cosine theta minus F sine theta, which balances the weight. Well, I changed the signs and all that, but anyways, I just tried to make it Just like the rules that we have, anything to the left is negative, and that's equal to minus mv squared by r, because that's the centripetal force, and then n cosine theta is positive. Okay, and these two are negative, so that's why you have that's equal to mg, because it's taken to the other side. So next, you have two equations, and I'm going to divide equation 1 by equation 2. So divide this whole equation right here, divide them, and then what I've done is I've divided each term by n. So the n will cancel out here, but here you will get f by n. Remember, f by n is mu. So that's why you have mu. Same thing happens in the denominator. And then when you divide the right hand sides, the masses cancel out. And then I've plugged in the numbers, because theta is given as 15 degrees. So I plugged in 15. Velocity is given, plug that in. And then you have to calculate, you have to separate the mu and calculate, which is so what I've done here. When you do all that calculation, you get mu is equal to 0.249. It's a little bit of calculation, but you have to be just careful about the components. And then you have this question where you calculate the work done on a 1550 kilogram elevator car by its cable to lift it 37.5 meter at constant speed. Work. Now there is also friction here. So you have to find the net force and multiply it with the displacement. So the net force is 15,305 newtons, which includes friction. Then multiply it with 37.5 to get the work. Then you're asked to find the work done by the gravitational force. Remember, it's moving opposite to the gravitational force, so when you're asked to find the work done by the gravitational force, it's going to be negative, because theta is 180 degrees and cosine of 180 degrees is -1. So that's why that's negative. And then what's the total work done on the lift is of course 0, because you're doing work against gravity and against friction. So when you take the net work, it cancels out, it's 0 joules. Here is this man pushing a crate up, and you're asked to find the work. So you have to remember that when he pushes the crate, he's also dragging his body up. So the force that acts on him is minus mg sine theta. It's acting down. And this is the force that he exerts on the crate. So that gives you the net force. Well, actually, he has to apply a force. So in this question, the man is pushing a crate 3.65 meter up a ramp, but he has to lift his body up too. Therefore, the net force he must apply is actually the force he exerts on the crate plus the force required to lift himself up, which is mg sine theta. So that gives 832 newtons, and then that multiplied by 3.65 gives 3035 joules. And you may ask, well, how do you get mg sine theta? That's because his weight acts vertically down, and when you resolve it into the horizontal component, you get mg sine theta here. In this question, a car's bumper is designed to withstand collisions, of course, and you're asked to find the average force on a bumper in stopping a car which is initially moving at 2 meters per second. So what really happens in this case is the kinetic energy of the car, or the change in kinetic energy of the car rather, is equal to the work done. So the work energy theorem. So let's put the kinetic energy of the car, the change in kinetic energy is equal to the work done. Work is force times displacement. So simple enough. Gives you 5,330 newtons. This is again a straightforward problem. Work is given, time is given. You have to find the power. Just make sure that time is in seconds. Here it is given in hours, so change it in seconds. And then it says, working at this rate, how long will it take to lift 2100 kilograms of bricks? So you know the power, work over time, and when you lift something, the work done is mgh. So that's why I'm using mass of the bricks times g times h divided by time. That will give you the time as 145 seconds. So thank you. I hope this was useful.